Hello, we're here today to talk about something called valence shell electron pair repulsion theory, otherwise known as VSEPR. But to start us off, I'm going to draw a picture. And you might know, based on your life, that this little 2D stick figure really represents a person. But you also know, based on your own experience, that in no way does that actually look like a person in 3 dimensions. Well, the same thing is true about the dot structures we've been drawing in class. The Lewis diagrams for molecules like CH4 and H2O are all representatives of molecules in only 2 dimensions. It's how we draw them on paper. Just like a stick figure doesn't really look like a person in 3 dimensions, the same thing is true with these drawings that we've been doing. What we're learning today is how to change this drawing and this drawing, which again are 2-dimensional drawings, into 3D. So we're going to figure out what the shape of molecules look like in 3 dimensions instead of just on paper. All right, so what that's called is something called VSEPR. So you should have this note sheet, and if not, you're going to just want to copy it down and copy down the table we're using. VSEPR stands for this: valence shell electron pair repulsion theory. And that's why we use the acronym VSEPR. Okay, it's kind of a mouthful. Valence shell electron pair repulsion theory. What you really need to know about VSEPR is it predicts the 3D shape of molecules. Now, a quick note about this. In order for us to predict the shape, I need something to start with. So you always need to start VSEPR with a correct Lewis diagram or dot structure. So let's go ahead and do our first example to show that. My example is going to be CO2. And I'm assuming at this point that you already know the steps for drawing a structure. Now, if you wanted to pause the video and practice that right now, you totally could. Otherwise, I'm just going to show you what the completed structure would look like. Okay, so once I follow the steps, the structure for CO2 looks like this. All right, let's talk a little bit about what this molecule would look like in 3D. Now, here's what you need to keep an eye on. This is all about electron pair repulsion. We know from past experience that opposite charges attract and like charges repel. Now, we know that bonds are made of electrons. So these are electrons here, and these are electrons here. Now, why is that important? Well, since those electrons have negative charges, and so do these, those electrons are not going to be next to each other if at all possible. In fact, the molecule is going to completely rearrange itself, so completely move the bonds around, so those electrons are as far apart as possible. Now, what's that going to mean? Now, this one's pretty simple. In order for this set of electrons and this set of electrons to get as far apart as possible, they're going to be in a straight line across from each other. And this is what our 3D drawing is going to look like. When we draw a 3D drawing, we use circles to represent the different atoms. So I'm going to use a circle here for my O, and I'm going to show the double bond just with those little bendies, and I'm going to use a dark circle for my C. Again, showing my bond. Now, what we look at for the actual shape is this right here. Okay, this right here is 180 degrees. So, what is that? Well, you're going to notice that all of those atoms are in a straight line. And so the name for that first shape is linear. All right, let's talk about our next shape. Okay, so our next molecule we're going to figure out the shape of is water, or something like water. And again, if you went through and drew the structure for water using the steps we learned this chapter, this is what your structure for water would look like. Now let's talk about what the shape of this structure would look like. All right, now we still have electrons here and here, and those are going to repel each other. But we also have electrons here and here. I want to show you what ends up happening in this particular case, because what's going to happen is those two lone pairs in the middle are going to kind of all be one big conglomeration of electrons, and those are going to repel the electrons in the bond. And I'm going to show you with a quick little example here. All right, so here is my structure. I'm going to go ahead and add a bond here. So if you look at my structure that's on the screen right now, I have the O in the middle and the two H's. And right now it looks like a straight line. But watch what happens when I add my lone pairs. Now they're representing lone pairs with these silly looking little things. You're going to see them here. I'm going to go ahead and add lone pairs to this molecule. And we're going to see what happens. I'm adding my two lone pairs. And I want you to look at what happened to that bond. Is it in a straight line anymore? It's not. So what ends up happening when we're talking about 3 dimensions is those lone pairs kind of repel the electrons in the bonds and push them down. And so they're no longer in a straight line. They look like this. Let's go ahead and draw this one. And that angle is usually at about 120 degrees, somewhere along there. And that's no longer linear. The name for this structure would be bent. All right, third shape. Third shape. We are going to do NH3. So again, if you were to follow all of the rules for drawing structures that you've learned in this chapter, this is what you would get as the final outcome. So notice a couple differences. Difference number 1, instead of just being bonded to 2 atoms, my central atom is bonded to 3 different H's. And there's a lone pair. So again, the goal of VSEPR is for all of those electrons around the central atom to get as far apart from each other as possible. They're going to repel. So let's think about what that would look like in 3D. I'm going to go ahead and put up my molecule again, and I'm going to start from scratch. So I'm going to go ahead and add my 3 bonds. So that's my N in the middle and my 3 H's surrounding it. All right. Now I'm going to go ahead and add my lone pair. And let's go ahead and twirl this one around a little bit and see what shape we get. So what happens, first of all, do you see that those bonds, I'm going to put it straight like this, they're about 120 degrees away from each other, okay, to get those bonds as far apart as possible. But instead of being straight out, you're going to notice that that lone pair kind of does the same thing it did with water. Do you notice that it repelled those bonds? So instead of being flat or linear, those bonds are pushed down at an angle. And that's all because of that lone pair taking up space. So the way we draw that is like this. There is my N in the middle. Here's an H, here's an H, and here's an H. The name for that is trigonal pyramidal, because it kind of looks like a pyramid. All right, next shape. The next shape we're going to do is going to come off of this example. So we're going to do CH4. So again, you would follow what you've learned in this class about how to draw structures, and this is what you would draw. And again, in 2 dimensions, it just looks like a flat molecule, a C with an H going to the left, right, top, and bottom. Here's the problem. In 3 dimensions, to get these 4 bonding sites, which are full of electrons, as far apart as possible because they repel, that actually isn't the best way for them to actually arrange themselves. Again, let's go back to the molecular shapes here. And again, I'm going to take everything off and start from scratch. So there's my carbon in the middle. I'm going to add 1 hydrogen, 2, 3, and 4. So take a look at this structure right now. I'm just going to kind of rotate it a little bit so you can see it. And that's kind of what it looks like. I'm going to move it around. I'm going to flip-flop it. And the one thing you would want to notice about this is no matter which way I flip-flop it, are you noticing that it's symmetrical. Every way I turn it, it looks the same, okay? So there is a name for this shape and a drawing for this shape that we're going to write down, and I just want to kind of get it like this. This is about what we're going to make our drawing look like. So our drawing is going to look like this. It basically looks like trigonal pyramidal, but it actually has a bond on top like that. The name for this shape is going to be tetrahedral. Tetrahedral. Okay, and the last shape we're going to be learning about is one that you don't come across quite as frequently, all right? The example I'm going to give for this is CO3, -2 or 2-. And again, this is a polyatomic, and this one's a little bit more complex. This is one that actually has resonance. So when I draw the structure for this, I'm going to pause or practice this. There's one structure. And then because I can put that double bond in multiple places, I would show all 3 possibilities. Now I know that's kind of hard to do on the small piece of paper you have in front of you, but I just want you to be aware of this. So that's my second option. And then my third option would be this one. All right, so we have that single atom, and again, what we care about are the electrons surrounding the central atom. I get that those oxygens also have electrons, but that's not going to impact the shape. We only care about the electrons around the central atom. So you notice that I have 2 single bonds and a double bond. All right, so let's remove this, and let's go ahead and get started. There's my central atom, 2 single bonds, and a double bond. Take a look at what this does to the shape. Do you all notice that this shape, first of all, our bond angles, excuse me as I try and twirl this a little bit, are exactly even. You've got about 120 degrees each between the bond angles. And then do you notice that this is completely flat? All right, so here's going to be our drawing for this one. And I'm going to show that double bond, but I'm going to remind myself that that's 120 degrees. Okay. All right, this is also called trigonal, but it's called trigonal planar because it's flat. Planar means flat. Okay. All right, so to wrap up, one thing you should be able to do is tell what shape a molecule is going to take by just looking at the dot structure. So how do we do that? It's by looking at the central atom and seeing how many atoms it's bonded to. So we're going to fill in this bond column to wrap up. Linear is either going to have 1 bond from the central atom or 2 bonds with no lone pairs. Think about it. 2 bonds, there's a double and double, so there's 2 bonds and there's no lone pair. And again, we're only talking about the central atom. All right, bent. Let's take a look at water here, bent. So how many bonds do we have? 1, 2. So 2 bonds, but how do I know it's bent instead of linear? There is a lone pair or more than 1 lone pair on the central atom. The next one, trigonal pyramidal. Tri means 3. 3 bonds, but how do I know it's a pyramid instead of flat? Lone pair on the central atom. That's how I know it is trigonal pyramidal. Tetrahedral. This one I think sometimes is the easiest because it's the only one that has 4 bonds from the central atom. So again, when I'm counting bonds, I'm saying how many atoms it's bonded to from the central atom, okay? And finally, trigonal planar, 3 bonds with no lone pair on the central